So let's keep going on with limits. So last time we were working on limits at infinity. We did one example. For this previous example, we took a numerical approach just so you can see how the numbers get bigger and bigger every time. Actually, for both sides, recall that when we have some situations like this, we have to look at both sides of the function and then determine whether both limits agree or disagree on both sides, so we can say, well, the limit exists or does not exist respectively. So we're going to move on to another example. On example number 4, limit of 4 over x minus 2 as x approaches both from the right and from the left. Well, so this time I'm not going to go through the numerical approach. In this case, I'm going to go through the graphical approach. Well, so we need to know how the graph of this function f of x, let's call f of x equals to 4 minus x minus 2. Okay, so how would the graph of that function look like? And you might remember we went over a couple of sections on graphs of functions at the beginning of the semester. Number 1, the parent function, the different graph of the parent functions, and then shifting, translating those parent functions. So number 1, before looking at the graph, any ideas on where this f of x equals 4 over x minus 2 comes from? What would be its parent function, by the way? That's my question.
Would that be 1 over x?
1 over x comes from 1 over x. And what's the graph of 1 over x? How does that look like? Okay, so we have yes, something like this, right? However, what is this negative 2 going to do on that graph?
Is it going to translate it 2 units to the left?
To the right. And what is that 4 going to do? Just some vertical compression. Well, the vertical compression is not going to make any changes to the horizontal, so I'm just going to go with okay, so that means there's a vertical asymptote at x equals to 2, right? So we're gonna get this graph, and that's gonna look like this. So we need to analyze both sides of the limits and then conclude about the actual limit at the value itself. So number 1, limit, well, let me just call it f of x for short. X approaches 2 from the right, and limit x approaches 2 from the left. Okay, so let's observe the graph of the limit. So we want to approach 2 from the right. So when we approach 2, where is this value going to? It's going to positive infinity. Okay? Alright, what about from the right?
Negative.
Okay, negative infinity. Alright, so let's observe these two values, these two limits. So we're looking at the limits from both sides, from the left and from the right. Now, what would be the limit f of x as x approaches plain vanilla 2? Not left, not right. Does not exist. Why is that does not exist? These two limits disagree, right? Do not match. So for this reason, D and E. Alright? So does not exist. Alright. Let's see what's next. Well, again, coming back to vertical asymptotes, well, you know the definition of a vertical asymptote, and well, depending on how we approach to those vertical asymptotes, the behavior could be the function increasing to really, really big. How big? Well, positive infinity, or decreasing to really small, which is negative infinity. And well, let's evaluate the following limits using that idea of asymptotes, which is very similar to very similar to what we did before. So in this case, we might want to recall the graph of the tangent function. Let me draw it for you. So the tangent function looks like this. Oops. with an asymptote, another asymptote, negative pi over 2, pi over 2, another asymptote, that's 3 pi over 2. So the tangent function has vertical asymptotes at all multiples of pi over 2. That is pi over 2, 3 pi over 2, 5 pi over 2, if we keep going, 7 pi over 2, all odd multiples of pi over 2. So, well, they're asking us to find the limit of the tangent function as x approaches pi over 2, but in this case from the left, only from the left. I don't want to see the limit from the right. So what are we going to do? We want to approach this value of x, which is pi over 2. We want to approach from the left. All right, where is that going to? Positive infinity. All right. Alright, so there's another approach to this problem. Okay, let me show you how we do. So, another way to see this is to write the limit as x approaches pi over 2 from the left, and writing this in terms of sine and cosine. So using identities, what's tangent in this case? Sine over cosine. Okay. Both functions, numerator and denominator, don't have any restricted domain. They are defined for every real number. However, overall, this rational, this quotient, is undefined for cosine x cannot be 0, right? Because if cosine x is 0, the denominator is 0, we will be getting some sort of undefined value. Well, so let's observe this cosine function. So let's analyze that on separate. So the graph of cosine, which looks like this, that's 2 pi, 3 pi over 2. This is pi, and this is pi over 2. Okay? Well, so here is the thing. We are going to approach pi over 2 from the left. All right. However, check this out. We're going to do so in a way that we get arbitrarily close to it. Now, those values that I'm shading here, what is the sign of those values? Positive. Okay, so the way we're going to evaluate this, well, number one, that's by direct substitution, that's a sine of pi over 2 over cosine pi over 2, which is, well, sine of pi over 2, which is 1, but approaching, so okay, I mean, cosine pi over 2 would be 0, isn't it? It would be 0. However, 1 over 0 would be undefined, and the undefined vocabulary is for functions if we were evaluating f of pi over 2, but we are not evaluating at that function. We are going, what we want to do is find out what is the value of y apparently getting hit when we approach pi over 2 from the left. We are getting arbitrarily close. By arbitrarily, let me call this arbitrarily small. But again, the signs of these values, how in a way that we get closest to pi over 2, isn't it positive? All right, arbitrarily small positive. Okay, now the question is, what happens when we divide a number by a really, really small number?
Big.
It gets big. How big? A million.
Like the smaller it is, the larger the number.
Exactly, because yes, divide by small, we get big. That means how big? Well, infinity. Positive infinity, because we are dividing by a small, arbitrarily small number. We're going to do more examples of this in the next section, so you get a better understanding of this. In the meantime, let's look. Okay, question. What if we wanted the limit of tangent, well, sine over cos, and that's x approaching pi over 2. But how about from the right and not from the left?
Is that equal to infinity?
Yes, plus positive infinity. No, well, you know what? Let me erase this. We don't need the plus symbol for infinity. That's fine. For positives rather. Well, so here we're going to have again sine pi over 2 over cosine pi over 2. However, so we're getting a 0 in here. Now the thing is, we are approaching now from the right. Do you see how we are getting arbitrarily small values from the right? But now, what is the sign of this y value? The value is in green.
It's getting bigger.
So yes, it's going to get big, but I mean, with which sign? Negative. So that means in this case, this will be divided by arbitrarily small, but in this case negative values. And well, divide by small, again we get big, but in this case with negative sign. So that's how we would get negative infinity. Now let's compare this result using the graph. Approach pi over 2 now from the right. Where is this going to? Does that check? Alright, so either way, so when you see a question like this on the exam or on the quiz, etc., use either approach, the arbitrarily small, big, I mean the arbitrarily positive or negative value approach, or the graph. But in this case, make sure to memorize or to know the graphs of the trigonometric function. So that's, if for some reason you get it the other way around, you write the graph of sec, oh no, not secant, cotangent instead. Well, just make sure you got the graphs down. One more, yes.
So how is it approaching negative if it's going up, if increasing from?
Oh yes, but these values of y, right here, what's the sign of these values of y?
That was a negative. But
Negative.
it's approaching in a positive direction.
So yes, we're approaching 0, but by means of negative, of arbitrarily small values, small negative. From the other side, we're approaching 0 as well, but by means of arbitrarily small but positive, because in this case, let me have those signs. Positive values versus negative values.
Okay,
All right?
So
Yep.
it'd be positive and negative depending on which side of the x-axis.
Exactly. So, and this reflects this graph right here, you know, going up to positive infinity, going down to negative infinity, going up to positive infinity, going down to negative infinity.
Okay, that makes
So either approach, and on the one hand we're using the actual graph of tangent, but in this case we're using trigonometric identities and the numerical approach. And you don't have to do a table, just this brief illustration right here to show how big or how small we get to that value.
Okay, thank you very much.
My pleasure. Number 2, limit ln of x. Okay, that's another graph we reviewed at the beginning of the semester. That looks like this, has an x-intercept at 0, 1, and also make sure to draw the vertical asymptote at x equals to 0. Alright, okay, let's look at that limit. So in this case we're approaching 0 from the left, from the right. Where is this limit going to?
0 to positive infinity.
It's going to be negative infinity. Alright? Negative infinity. It's going down to negative infinity. Now, tricky question. What would be limit of f of x? Well, ln of x as x approaches 0 but from the left. What would be the limit?
Wouldn't that be positive infinity?
Positive infinity. Also negative infinity. Does not. Why is it does not exist? There's there's no graph from the left to right, if there's no graph, there's no trend of values, there's nothing, well, just D and E. Alright? Okay, let's move on to, I guess, the next topic, the next section. So, and okay, so we are going to calculate limits using the limits laws. Well, I mean, these limit laws, it's not something that you have to memorize them. I mean, symbol by symbol, parenthesis by parenthesis, bracket by bracket. No, actually, all these symbols that we're seeing that you have on your textbook, it's actually what's going on our heads when we have a limit problem and we are actually going through the problem. You know, but essentially, whenever we have the limit of a sum, this is the sum of the limits, and same for the difference. The limit of a constant times a function, that's the constant times the limit of the function. The product rule for limits, the quotient rule for limits. But very important that the limit in the denominator is not equals to 0, because if the limit in the denominator is 0, well, we're in trouble then, right? So that's going to be on the function, for the function, but doesn't, well, depending on how we get to that 0. Same for the powers. What else? The limit of just a number is the number. The limit of x, plug in the value x at a, well, that's going to be a. And well, in this case, we're no longer going to go through the graphic, or well, in some cases we're going to go to graphic, but we're going to do the direct substitution property. So what we're going to do is plug in the value, x is approaching 2 in the limit, and well, whatever value we get, that's our limit. Great. Otherwise, well, we will have to do a bunch of algebra. I was going to say some algebra, but no, it's going to be heavy on the algebra. But now, from this graph right here, let's use the limit laws and graphs of f and g to evaluate the following limits. Well, so this can be rewritten as the limit f of x as x approaches negative 2 plus 5 times the limit of g of x as x approaches negative 2. And well, in this case, we're going to get the results from the graphs. Well, we have the graph in red that represents the function f, and we want to see the limit as x approaches negative 2. So negative 2, which is right here, negative 2. Oh, be careful. What would be the limit as x approaches negative 2? Notice we have this hole and we have this point in the middle of nowhere. So what would be the limit? 1, right? So we're getting, in this case, close from both sides. Actually, not stepping at that value, not stepping at that point. If otherwise we were asked to find f of negative 2, that'll be instead this point in the middle of nowhere, and it would have been 3, not the value where the hole is. So that's 2 plus 5 times the limit of g of x. Well, for g of x, let's look at the graph in blue, which represents the graph of g of x. And well, at negative 2, okay, go negative 2, what's the y value being hit? Negative 1, so that's 2 minus 5, negative 3. Alright. Let's look at another example involving a product rule. So, number 1, this will be the limit of f of x times the limit of g of x as both limits approach x equals to negative 1. So let's look at the graph of x. That's the graph in red, and we want to approach to negative 1. So,
over the previous question, why is there
what's the coefficient?
No, well, why is it a 2?
This one?
Yeah.
Oh, so for f of x, which is the graph in red, as we approach negative 2, oh no, that's supposed to be, yes, that's 1, yes. So that's negative 4, thank you. Yeah, because I was repeating the idea of evaluating the function, so that number stuck in my head. All right. Okay, so f of x approaching x equals to -1. So we want to approach -1 for f. Well, what's the y value being hit here?
1.5.
So, oh, there's a typo actually. It should be a +1. Okay, so never mind. Let's change sides. Okay, so approaching 1, what's the y value being hit? 2. Okay, so that's 2 times. Okay, limit g of x as x approaches also +1. And oh, check this out. Well, do you see how this limit is going to two different values of y? From one value of y from the left, another y value from the right. So what would this be?
Would it be -2?
Because from the left, the limit is.
Just -2.
What about from the right?
-1.
Do the limits agree? No, so d and e, right? 2 times d and e, well, it's not like we do operations with d and e's, of course, so that's d and e. Okay, does not exist.
Why didn't you just make it
-2. Oh, because in this case we want the limit as x approaches 1, like
Since there's 2.
exactly. It's plain vanilla 1. If in the beginning I said 1 from the left, for example, this would have been 2 times -2, and we would have gotten a -4. But in this case, both limits disagree. So plain vanilla +1, it's not going to be. It's going to be a d and e. So one more. Limit f of x. X approaches 2 over limit g of x. X approaches 2. Let's look at one function at a time. So f, which is represented by the graph in red. So approaching x equals to 2, what's the limit? Oh, I mean x equals to 2. That's like 1.5. And what about g of x approaching 2? Oh, 0. We're in trouble here, right? We're in trouble. And we're going to use the arbitrarily small positive or negative approach. So in this case, okay, what do I have in? Okay. Now the thing is, how do we get this 0? How do we get that 0? Okay, let me erase this part and then explain it over here. Okay, so how do we approach to this 0? We can approach from the left, but isn't this arbitrarily small negative? Right? And this is arbitrarily small positive. So we're getting two different approaches, a positive and a negative. So in a similar way, for this reason, D and E, because this 0 is approached, it's approached by means of arbitrarily small positive and negatives. All right. So for that reason, we will be getting two different values. In other words, by approaching arbitrarily small negative, so we divide by a small negative, what do we get?
You get big number.
We get, but negative big number, that's negative infinity, right? What do we get when we approach arbitrarily small positive? Positive infinity. So both side limits disagree. One is negative infinity, one is positive infinity. Alright, so for this reason it's a D and E in this case. Alright. Other examples of direct substitution. So this is just like, yes,
Why would it be arbitrarily small and not just 0?
So, yes. So here, we're approaching 0, right? From the left, we're approaching 0, but by means of negative numbers. Every time small enough until we get to that value. So, but in this case, because that 0 is in the denominator, what do we get when we divide by small negative? Big positive, right? That's positive infinity. Now, let's look at the other side. What do we get when we approach that 0, but from the right, that is by means of arbitrarily positive numbers. So we divide by a positive small number, what do we get?
Negative small.
So we divide by, we are approaching by means of a positive small. So when we divide by positive small, we get positive big.
What?
So we are dividing this 1.5 by a positive small. Positive over positive. What's positive over positive? Positive, right? What's positive over negative? Negative.
So, and just to clear it up really quick, if it was like we were doing the limit of x to like either direction, we wouldn't get d and e, right?
Exactly. So if we had like the graph like this, instead, on both sides we will be approaching arbitrarily positive, getting to the same infinity, and in that case we would have a limit defined, not like in this case, which is d and e.
Okay.
All right. Okay, examples on how to evaluate limits. Finally, when we just use the substitution rule, all we do is simply 2 times 5 squared minus 3 times 5 plus 4, and hopefully we get a really nice number as the final answer. So that's the replacement theorem, or the direct substitution rule. Okay, so 5 squared, which is 25 times 2, so that's 50 minus 15 plus 4, and that's 39, and we're done. We're done. That means that if we were to look at the graph of this quadratic polynomial, when we approach 5 from both sides, we would have been getting the y value of 39. Letter B. By direct substitution, just substitute -1.
But it has a positive next to it.
Yes, it's not going to matter in this case. Either way, it's fine, because in this case, x squared plus 3 in the denominator is never equal to 0, so we're not going to have any vertical asymptotes, so we can look at the graphic approach. So that's going to be -3 over, that's 1 plus 3, which is -3/4. And well, those are like very direct limits, like everything works nicely and we get a final answer. However, let's see. Let's look at a limit that we looked at, I think, last time or last week. Well, I mean, sometime last week. So we did this limit. When we were going over the concept of limit, how evaluating a limit is not just plugging in the value of x. So yes, I mean, in terms of calculation, that's what we do. But that's the same thing we did when we evaluated functions. But recall that those are essentially two totally different concepts. A function is defined or undefined, and that tells us whether we can stand at that point. But on the other hand, the limit is to find out which value of y are we apparently getting hit when we approach some certain value of x on the function. And well, so let's try direct substitution. So last time what we did is to evaluate the function. We found out that the function was not defined for a certain value. We looked at the graph. We had a linear function with a hole, with a removable discontinuity. We will discuss discontinuities later, more in depth. But in the meantime, let's use the direct substitution theorem in here. So what we do is, number 1, 1 squared minus 1 over 1 minus 1. This is 1 minus 1 over 0, and this is 0 over 0. Well,
So that's a D&E now?
this is actually good. Whenever we get 0 over 0, this is good because this is an indeterminate form. Not like the other ones, like a number over 0. No, that's not an indeterminate form. When you get a number over 0, that's where we need to look at the limit on both sides of the graph, whether with a graph or with a table of values, and then see how we get to that value of y, either positive infinity or negative infinity. But in this case, 0 over 0 is great because this means that we need to do algebra and simplify this limit expression. So let me go back to limit x squared minus 1 over x minus 1. X approaches 1. So we need to do all the algebra techniques that we have available to try and simplify this. Okay, so what about the numerator? We have this x squared minus 1. Isn't that a difference of squares that we can simplify as x plus 1 times x minus 1 over x minus 1 as x approaches 1. And now check this out. The idea of doing all the algebraic techniques available to simplify the expression in the limit is to cancel these terms. When we cancel this x minus 1 with x minus 1, we're actually eliminating that part of the algebraic expression that is causing this 0 over 0. Once we're done cleaning this up, this will be the same as getting limit x plus 1 as x approaches 1. And at this point we can do the direct substitution, and we will no longer get a 0 over 0. That's actually 1 plus 1, which equals to 2. Alright? So what other algebraic techniques should we know? Well, pretty much everything. All your factoring techniques, all about simplifying complex rational expressions, all about multiplying and dividing by actually conjugates of algebraic expressions. I'm going to go over an example of every single case just so you can see how things work in this case. And well, that's pretty much, here's a list of strategies. Well, we can factor polynomials. We can also expand this, and we may get actually exercises in which we will have to expand, like this one right here. Do other manipulations, algebraic manipulations in general. Alright, so number one, let's evaluate the limit right here. So by trying direct substitution, we get 3 plus 0, quantity squared, minus 9, over 0. So 3 plus 0, which is 3, and then 3 squared, which is 9. And what do we get?
0.
Which is good. 0 over 0 is good. That means that we can do some algebraic technique, manipulation, to cancel those factors that cause this 0 over 0 in the same way that we did before. So let's see how we go about this. Well, number one, I'm going to expand the binomial in the numerator. However, there's a couple of ways to go about that expansion. Number one is by writing the x plus h squared as 3 plus h times itself. However, and then foiling. However, that might take a little time to do the foiling. Instead, I'm going to use the square binomial formula that you may have seen before. So whenever you have something like a plus or minus b, quantity squared, so we square the first term plus or minus, well, depending on the case that we're given, 2 times ab plus b squared. All right. So that's the approach I'm going to take over here. But of course, if you're used to do the foiling method, by all means do the foiling method. You should get the same result. it's valid on the quiz or on the exam. I mean, there's always more than one way to solve a problem, so by all means. Limit, so that's 3 squared, which is 9, in this case plus 2 times these two factors, that's 6h plus h squared. Okay, that's the expansion of this binomial, minus 9. And well, let's go ahead and simplify whenever we can. For example, we can cancel these two 9s here, and then from here we're left with limit 6h plus h squared over h as h approaches 0. Now we can further simplify this expression because notice the numerator has a common factor of h. So that's h times 6 plus h over h as h approaches 0. Now check this out. At this point, we may divide out these two h's. Aren't those two h's the ones that are causing trouble in the limit, are giving us a 0 over 0? Okay, so that means we're safe. We're safe now. So that's limit 6 plus h as h approaches 0. So we may go ahead 6 plus 0, and we will no longer get a 0 over 0. We will get an actual value for the limit. Alright? Okay, let's look at example number 2, number 2 and example 3 right here. Well, this one is going to be a little bit more complex. So what are we going to do? Well, of course, as usual, let me do the replacement theorem, the replacement or the direct substitution. So this would be the square root of 0 squared plus 9 minus 3 over 0 squared. Okay, 0 squared, which is 0. 0 plus 9, isn't that the square root of 9? Minus 3 over 0. And what is the square root of 9? 3 minus 3? 0 over 0. What's this? This is good. This means that once we do the algebraic manipulations here, we will be able to factor out or to divide out those factors that are causing trouble in our limit. Okay.
What happens if it doesn't get 0 over 0?
Then we will have to look at the techniques that we did before, like the graph, to see where is it going, maybe to negative infinity and positive infinity, or both positive infinities or both negative infinities. So we need the graphing approach or tables. All right. Well, so in the example at the top, we factor the differential squares. In the previous example, the one above, we needed to expand the binomial. All right. Guys, you have any questions here? Yes.
What do we do from medium to square here? From medium to square, like d plus 3 whole square minus...
Right here, complete the square?
Yeah.
Well, completing the square, we would use it if we wanted to, when we have a trinomial and we want to turn it into a perfect square trinomial. However, here we have radicals. So this is what we're going to do. For the situation, we're going to multiply numerator and denominator by the conjugate. And the conjugate of the numerator is exactly the same expression, but instead of having a minus, the conjugate uses the opposite sign, which is plus. Okay? All right, I know. It's gonna this looks like a hell. Check this out. Looks like a hell to do this, right? However, you don't have to do the foiling 4 times and write all these many terms, because check this out. Isn't this really okay, let me put parentheses around this. Doesn't that look like A minus B, A plus B? Isn't it? a product of conjugate binomials? What is this a minus b times a plus b, by the way? Where have you seen this before? It's the factor form of a difference of squares. So we're going to do a difference of squares backwards. So something like a squared minus b squared. Instead of doing all this madness of distributing 4 crazy terms, well, use the limit. So it's going to be the radical squared minus the b squared, which is 3 squared. And over here, I know that it looks very tempting to distribute, right? But don't do the distributions. You'll see why. As a side note, okay. So multiply across these two. That's t squared square root. Oops, no. T squared times the square root of t squared plus 9 plus 3 t approaching 0. Okay. Let me write down a note right here. Do not distribute. You'll see why in a second. Okay, number 1. What happens between the square and the radical? Don't they cancel away? And 3 squared is going to be 9. Alright, so that's equal to the limit t squared plus 9 minus 9, the whole thing over this product. And check how these 9's cancel out. I'm going to continue here. So we're left with t squared over t squared plus 9 plus 3 as t approaches 0. Do you see where we're going here? Do you see how canceling this t squared over t squared solves the problem, eliminates the factors that cause this trouble 0 over 0, and this will be limit square root of t squared plus 9 plus 3 t approaches 0. Once we get rid of those factors that cause the 0 over 0, we can say that we're safe. We're safe to do the direct substitution once again, and this will be 1 over the square root of 0 squared plus 9 plus 3, that's the square root of 9 plus 3 plus 3 in the denominator, which is 1 over 6. How about it? Do you see all the algebra that we need for this kind of problems? Well, guys, for the next exercise, no, actually we can do it in 6 minutes. Why not? Let's go ahead and do it. Yes, let's just do it. Okay. Number 1, direct substitution. Yes. Okay, so 2 over 7 plus 0 minus 2 sevenths over 0. That's 2 sevenths. That's a 0 over 0. This is good.
Yes, perfect.
It's perfect because we can use algebraic manipulations to get rid of that factor that causes trouble and then be in a safer place. Do direct substitution once again, and we got this. However, well, let's do a mini review of what we have done. So we have done some factors, we have done some expansion, we have done some multiplying by conjugates, we have complex rational expressions here. Think of this h as an over 1. So we will multiply numerator and denominator by the least common denominator of all the denominators that you see in the complex fraction. Well, we don't need to write the 1. However, one of the denominators is 7 and 7 plus h. So let's go ahead and distribute. Oh, because this 7 is one denominator. And this 7 right here is another different denominator. It's like having something like 1 over x plus 3 plus 1 over x minus 3. Those are two different denominators, right? So, okay, careful when distributing this. Number 1. So what happens when we distribute this 7 times 7 plus h? Don't this 7 plus h go away? Leaving us with 2 times 7, which is 14, right? So this is limit 14, simply 14, and then minus, okay, what happens when we distribute this? The 7's cancel, leaving us with 2 times 7 plus h. 14 plus 2h. So let me do 2 times 7 plus h, and then I'm going to do the distributive property. And then over here, we can just multiply this across. And again, just like the previous example, don't distribute. Don't distribute. So that's 7h. 7 plus h. Alright, so let's do the 14 minus 14 minus 2h over 7h times 7 plus h as h approaches 0. Well, 14 minus 14, and that's the limit, negative 2h over 7h times 7 plus h as h approaches 0. Now, do you see what's happening here? Cancel out the h's. When we cancel these two h's, that 0 over 0 is gone. This means we're safe. Negative 2 over 7 times 7 plus h. We may go ahead and plug in the value of h equals to 0, and sure, we're going to get a value. Yes?
Oh, wait, never mind, sorry. I did it wrong.
Never, oh, that's fine, that's fine. So negative 2 times 7 divided by 7 times 7 plus 0, which is negative 2 over 49. We're going to do more stuff next time, guys. So